Hey guys, Dylan here, and I will be talking about thermodynamics today. I hope you guys are doing great. Um, so let's define thermodynamics. Thermodynamics is the study of relationships between energy and work associated with chemical and physical processes. This eventually can be determined and eventually predictable, which is awesome. To determine these relationships, we need to know the topics of spontaneity, entropy, the second and third laws of thermodynamics, and free energy. Some of the key terms that we'll be using in this is an isolated system, an open system, a closed system, and STP. STP is simply an acronym standing for standard temperature and pressure, um, which you can look up on your own in this chapter. And then an isolated system is the that a system cannot exchange energy or matter. Open is the exact opposite of that, that a system can exchange both energy and matter. And then a closed system is that in between of when a system can exchange only energy but no matter with its surroundings. So that will be helpful for a lot of our explanations and stuff later on. Right here, we'll talk a little bit about the phase changes that we can see different solids and liquids and gases go through and substances. So right here in the middle, a little bit, you can see the triple point in between all three of the different phase changes. This is an exact point of when temperature and pressure are at a specific point in which you cannot tell the difference between a solid, liquid, and gas. Can't believe it's even possible, but it definitely is. It's pretty cool to see that. You can see that the lines extending from here and here are pretty definitive in between solid and liquid and solid and gas. However, it does get a little fuzzy once we get up to here in this portion between liquid and gas. That starts here at the critical point, which is when the liquid phase is being heated to a temperature and its density is constantly um, increasing, while the gas that is being given off by the liquid, that its density is constantly being given um, less, which means that the liquid is coming up and the gas is going down. And at the critical point, it makes it fluid so that it's constantly interchangeable at that exact pressure and temperature. So that is called a supercritical fluid. And then past that point, it's a little hard to understand to tell the difference between gas and liquids. So we delve into spontaneity to get to the next part in this discovery process. A spontaneous process is one that occurs naturally under certain conditions, while a non-spontaneous process is one that needs to be driven from an internal source of energy. Um, so on the right here, you can see that the ball is naturally going to roll down the hill. We don't know how it got started that way because we don't need to know, but we know that it's going to go all the way down the hill. However, the non-spontaneous down here at the bottom is we can see it going up the hill. We don't need to know where it came from, but we know that it will need continual energy to get up the hill. If the push was hard enough, then definitely it's going to go all the way up there. But if it's not, then it's going to naturally, spontaneously roll back down the hill. So if you think about this kind of more, a little bit more in nature, when iron is left out and exposed to Earth's atmosphere at STP, then you can see that it will rust. However, without chemical interactions in the reverse direction, it is not even possible for that to even be seen. Similar Similarly, ice melting at the normal room temperatures or STP, um, ice will melt, but liquid ice will never go back right into the reverse direction. So if we move on from there, we can see a little bit of the dispersion of energy and matter. So if everything is at STP here, and the left bulb you can see here is full of matter, the ideal gas. Once the stopcock is open, it rushes to the other side spontaneously, goes into both, but the gas goes into both with the stopcock open, and you can see that it's at equilibrium here. The same STP is going on at all of the um, interactions here. However, we know that since this was a vacuum, because there's nothing in there, there's nothing in there, um, and nothing was exchanged, that nothing without energy or another outside source, all of this matter is not going to go into that side. So we know that. So we need to move on and know that there's some things that just can't be done the other way. So we'll move on to entropy, which is the each energy configuration probability. So we'll watch a short little video by Ted Ed.
Consider two small solids, which are comprised of 6 atomic bonds each. In this model, the energy in each solid is stored in the bonds. Those can be thought of as simple containers, which can hold indivisible units of energy, known as quanta. The more energy a solid has, the hotter it is. It turns out that there are numerous ways that the energy can be distributed in the two solids and still have the same total energy in each. Each of these options is called a microstate. For 6 quanta of energy in solid A and 2 in solid B, there are 9,702 microstates. Of course, there are other ways our 8 quanta of energy can be arranged. For example, all of the energy could be in solid A and none in B, or half in A and half in B. If we assume that each microstate is equally likely, we can see that some of the energy configurations have a higher probability of occurring than others. That's due to their greater number of microstates. Entropy is a direct measure of each energy configuration's probability. What we see is that the energy configuration in which the energy is most spread out between the solids has the highest entropy. So, in a general sense, entropy can be thought of as a measurement of this energy spread. Low entropy means the energy is concentrated. High entropy means it's spread out.
So that was a really helpful tool that we got to see and use. If you have any other questions, please let me know, and I'll post that link again in the page that I give to you guys for questions. And to move on, microstates, again, is the specific configuration of the locations and energies of atoms or molecules that comprise a system. And this was kind of found out by Ludwig Boltzmann, um, who made his own constant. And microstates, just to let you know, is indicated by W. So moving into a little bit of how to calculate the probability of microstates, as we take the number of boxes. So in this case, we have two, and that's our base number. And then we take the number of particles, and that is our power number. So in this case, we'll take 2 to the power of 4, and then that equals 16, which there's 16 different configurations or W or microstates that this substance can be in with one another. So you can see um, that this is an example of all the different configurations that we have here. And then we'll move on. So the different amount of microstates correspondingly increases with as the entropy increases. So you can see here from the solid that it goes up, and the number of microstates are increasing as you move up with the solid to liquid to gas, um, which is pretty cool. Um, and then next, we can see here, again, just a little bit of the phase change, and then the energy input that's being put in. At that the phase changes are here at the plateaus, while the energy is kind of being immediately here at C and E, and then these are the actual results of these phase changes. Um, so if we move on to the second law of thermodynamics, we can see that the entropy of a closed system is always increasing. So then, say if we're the system and then everything around us is surrounding. Wow, that actually means like everything surrounding us. So that must Me plus everything surrounding me is obviously the universe. So right now we're impacting the universe, which is crazy. Um, so you can see here from hotter to cooler and cooler to hotter, those two changes, you can see heat, which is indicated by Q, is changing in the system and the surroundings in the negative to positive state here. So we have to ask ourselves: are these spontaneous, and are these adding or decreasing to the entropy of the universe? So we know that in hotter to cooler situations, it is always spontaneous, and that it does increase the entropy of the universe. However, cooler to hotter means that it is not spontaneous, and that there is constant decreasing of the universe. But say if I was equal with my surroundings as my temperature, then neither it would not either be spontaneous nor would it be decreasing or increasing the entropy of the universe. It would be constantly reversing and interchangingly be giving off entropy and spontaneity, and then also the reverse of that. Here's a problem. This is the third law of thermodynamics. We'll watch this little video that kind of explains it. Kind of cool.
The coldest place in the universe is the Boomerang Nebula in the Centaurus constellation. At minus 272 degrees Celsius, or 1 degree Kelvin, it is only a single degree above absolute zero. Here on Earth, scientists have been able to get even colder than that by using lasers to cool individual molecules of sodium and potassium to 500 nanokelvins, but even they couldn't get to absolute zero.
So that's pretty crazy that we can do that here on Earth. Here's problem 3. So we'll move on to free energy. Um, you can see that free energy is a reliable indicator of spontaneity process. So this is the general formula that's attached to free energy and how to calculate it. You can see how it depending on where it is on the scale, you can definitely see that it affects the spontaneity and non-spontaneous reactions. Here's problem 4. This is just the interactions of temperature and spontaneity. This is really important for understanding the results of your calculations. As you can see on this screen, this is just an easier format for me to look at and understand that chart that we said before. So you can see where it crosses in between spontaneous and non-spontaneous, and the conditions that need to be met for um, each delta system that you have. Here's another problem. Here's problem 5. And then here we go at free energy and equilibrium and how they kind of interact with each other. And then as we move on, this is problem 6. Here's a little bit of the um, links that I wanted you guys to know that you have access to. There's the quantum casino there, right there, and then there's the chemistry textbook. Thanks, guys.